In this introduction, we will be describing the main output of FluoroMatch and FluoroMatch Flow, especially focusing on the annotation evidence and scoring. For further information, please see the scoring document provided with FluoroMatch. Before we begin, I'd like to talk about the two versions that are currently available. The first is FluoroMatch and the second is FluoroMatch Flow. FluoroMatch Flow is the recommended version, and the output table that we will view today is from FluoroMatch Flow. The major difference between the two is that FluoroMatch is for use if you have your own data processing workflow and want to simply annotate features which have already been peak picked and filtered. FluoroMatch Flow covers all steps of the PFAS annotation workflow from file conversion to annotation and scoring, and hence is more user-friendly. We recommend FluoroMatch Flow for most users. To access the FluoroMatch Flow table, you will need to find your output folder. Open the output folder and find the file that has FIN in the naming. If you don't have a file with FIN in the naming, an error has occurred and you'll need to watch the troubleshooting videos to determine where the problem is in the workflow. Let's get started. I'm going to go column by column and break down the information found in this table. Hopefully this video will answer the questions you have in an understandable way and make this heavy load of information more accessible. In this first column, labeled Score, you'll see the score ranking inferring PFAS assignment confidence and what types of evidence are available for that assignment. The score does take into account evidence from the KMD plots, but that is only one line of evidence it accounts for. In the column named Series Type, you will find any molecules belonging to a certain series. For example, rows 2 through 12 are all part of series 114. This means that the molecules all have the same normalized mass defect to CF2 and are spaced out by intervals of 50 Daltons, which is the normalized mass of CF2. In other words, series 114 is a unique and arbitrary number referring to the fact that all the molecules may belong to the same CF2 series based on exact mass. Note that multiple types of series may exist in a dataset, for example, molecules with CF2O repeating units. Members within a series are all ordered by mass and therefore the number of carbons found in them. This can be shown by taking a look at the formula column. You'll see C6, HF11O2, C7, C8, C9, C10, C11, and C12. If you see two molecules with the same number of carbons, there is a chance it could be an example of branched isomers and straight-chained isomers, or there is a chance it could be a false negative. The next column that we will discuss is Name or Class. This column tells you the names or classes of molecules that FluoroMatch has MS-MS evidence or fragmentations for in our database. In the case of a class, you can find the specific structure by looking at the formula or SMILES column. There will be some blank cells, but this simply means there isn't recorded MS-MS evidence, which can be used to assign a structure. Looking back at rows 2 through 12, you'll see that there are two identified as PFCA, perfluorinated carboxylic acid. While we can't be sure that the identification of these two leads to the rest in series 114 also being part of the class PFCA, just with differing number of repeating units, we can use this assumption as a starting point for identification. Another clue that this could be in the same class would be to look at the exact masses. Take a look at row 7. It is given a score of C+, which means there is no MS-MS or fragmentation evidence for this molecule, but the exact mass increase from C6 to C7 is 50, which would be the difference of the additional carbon fluorine repeating unit. The next column is formula, and that tells us the formula of the particular feature in question. In the column labeled smiles, you'll find a smile structure for the molecule. You can take a look at the scoring to see the confidence of the identification. Scrolling down to rows 33 and 34, you'll see scores of A and B+. Scoring of A denotes a very confident identification for this chemical structure, and you can then use ChemDraw, Marvin Sketch, or any other drawing tool to give you a visual of the feature. The mass charge column is very helpful. Sometimes, if there is no formula, you can still infer a candidate formula if it is a member of a series with a suggested formula and the mass falls into the series intervals of 50 Daltons apart. For example, if you have a mass that falls within a series and no formula, take a look at the formula before it. If, for example, the mass to charge of the one before is 600.6, and the formula is C8F20O3, and this one is 700.6, then the formula is 2 50 repeating units off, so a good candidate could be C10F22O3. The retention time column should follow a time order in the homologous series. Once again, taking a look at series 114, you'll see the retention times increase with each feature. 1.4, 4.7, these two are off, 5.9, 6.4, 7.04, 7.74. The exception here, like I said, are rows 4 and 5. This could indicate that these are branched or straight chain isomers or false positives, which would not belong to this series. In this case, because the mass is slightly off from 5 ppm tolerance on our instrument and they don't follow the retention time order, they are likely false positives and do not belong to this series. The adduct column simply shows the adduct. Right now, we only have negative adducts in our library, but in new releases, various positive and negative adducts may be included. The column labeled unique indicates whether the molecule is the only name given by MS-MS. If there is no name given, but a formula is given, the column indicates whether the formula is unique. If it is given a name or formula that is not unique, the cell will read no. If there isn't a name or formula given at all, it will have an NA in the cell. Score description is simply a description of the score. It gives you a little bit more information. If you want to go back down to this score of A in row 6, it tells you that it's a confident ID. There are class-specific dominant fragments observed along with the exact mass and 2+ in the homologous series. In column A, labeled row ID, you'll find a value that is related to the MZMine peak table. If you want, you can go back to the MZMine file and see how these peaks were integrated. Columns B and C, labeled row MZ and row retention time, give the specific mass to charge and retention times for each feature. In column D, labeled row number, you'll find the number of peaks detected before gap filling occurred. In column E, ending in peak area, this gives the peak area related to the relative abundance of the feature. It's important to note here that each sample in your study will have its own column. In our study, we only had one sample, but if you have 5 samples in your study, columns E, F, G, H, and I will all have this information ending in peak area with the name of the sample in front of it. In column F, this information is not important, so we can move forward. The next column of our example data set is labeled ID ranked. You'll find the score for confident identifications. Within each cell, the contents will start with a number, followed by an underscore, next an identifier, a way to name it, and a smile structure. With the smile structure, you can copy and paste it into a drawing software to get the structure. It's important to note in this column, the naming tells where the identification comes from. Let's take a look at cell G3. First, you'll see 1 underscore. This means the sample was confidently identified. Confident identification means that the exact mass and selected fragment ions observed in standard for this PFAS class were observed. Next, the class name is given, PFSA. The next piece of information is whether the identification came from standards or literature. If labeled standards, like this sample is, the identification is based on fragments observed in the experimental data-based dominant fragments observed in PFAS standards of the same class. If it is labeled literature, the identification is based on experimental fragments, which were also found as dominant fragments in spectra annotated in literature for a PFAS of the same class. Next, you'll see a multiple Y or a multiple N. Multiple Y means yes, there were multiple standards for that class. Multiple N means no, there was only a single standard for the class. Then you'll see the formula, the smile structure, and last, you'll see the adduct. Now to break down the number underscore ranges. Anything labeled 1 underscore is confidently identified utilizing a rule-based approach using standards. Anything labeled 2 underscore is currently only for thermo instruments. It is a confident annotation by all ion fragmentation. At this point in time, there is not a 3 underscore, and a 4 underscore means an exact mass was found. In the next column, labeled intensity ranked, you'll find the summed intensity of the annotated fragments. For the features that have more than one annotation, you will find those additional intensities as well. Sometimes you'll find that the intensities are exactly the same, which means that 2 or more structures are possible with the same exact mass and the same fragments. An example of this would be branched versus straight chain PFAS. An example like this can be detected in cell G10. You'll see that there were multiple branched standards used to identify this compound. The column labeled class at max intensity simply tells us the class of PFAS with the highest summed fragment intensity. The column labeled adduct at max intensity shows the adducts. At this point in our development, our software only supports negative polarity. Future goals are to add additional adducts and positive polarity. Only one class. We see in this column if there are multiple hits. If the cell reads no, you can go back to the column labeled intensity ranked to see the intensity of the summed fragments from the 2 or more annotations found. In the next column, labeled potential IDs, you'll see potential IDs of compounds based on MS-MS spectrum of class standards. In this case, if the exact mass and any fragments from the class-based standards is observed, the feature receives an annotation. It's important to remember that these are only potential IDs, as the dominant or characteristic fragments for that class need not be observed. This notation follows the same convention as in column G, labeled ID ranked. In the column labeled frags, you'll see the fragments that were found for each annotation, both for confident and less confident hits based on standards. Fragments separated by pipes show that these fragments were found for different annotations respectively. You'll see here that we have 2 separated by a pipe. Fragments separated by pipes show that these fragments were found for different annotations respectively. 2 columns over, you'll find the names of the files where those annotations can be found. In the next column, labeled num frags, this simply shows the number of fragments found. You may notice that some of these have multiple numbers in the cell divided by pipes, and that tells us that these fragments were also found in multiple annotations for the feature. The number of pipes found here should match the number of pipes in the tentative annotation column based on standards. Like stated before, in this column, labeled Files, you'll find the file name for the annotation and associated fragments. If there are multiple annotations found, the files which have the highest quality match are divided by pipes in the same order. This column, labeled Predicted Frag IDs, contains annotations based on predicted fragments from the EPA master list of about 7,000 PFAS. Fragmentation is based on substructures. For example, all compounds with a sulfonic acid group will be assigned SO3, SO3H, SO3F, etc. These are also tentative annotations. You can always take the SMILES annotation copy and paste it into ChemDraw, Marvin Sketch, or any other chemical drawing software. The naming of this column is slightly different in its form, so let's take a look at cell P3. The first thing you'll see is DTXSID, which is the identifier that the EPA uses in its Chem dashboard. Following is the preferred name of the compound. Next, you'll find other identifiers to help look up the compounds, such as the CAS registration number, the INCHI key, the IUPAC name, and this is a SMILES structure contained in the EPA master list. And then you'll see the canonical MS Ready SMILES. This is the one you'll want to use when looking for the structure. And last, you'll find the molecular formula for non-adduct. In the next column, labeled Frags, you'll find the different fragments based on substructures. This particular column gives more possible fragments than the predicted frags column and hence can be more informative. The column labeled NumFrag1 is how many fragments can be found. The next column, labeled Files1, gives the name of the sample file where the fragments were found. The next two columns, labeled Nominal Mass and Mass Defect, are not super important columns of information. They are provided if you want to plot nominal mass against the mass defect, which is non-normalized or normalized to CF2, and the column labels let you know which one is which. In this column labeled Kendrick Mass, this is the mass with the defect normalized to CF2. This means that instead of the mass of C being 12, the mass is normalized to CF2, which is 50. The columns labeled Nominal Kendrick Mass and Kendrick Mass Defect provide these data sets and can be used to make a visual using Excel's graph features or other graphing software. The next column, labeled KMD Group, simply means compounds with the same number group in this column fall within the same Kendrick mass defect. In the column labeled Homologous Series, you'll see samples that come from the same group. This is a very important column for finding PFAS series. For example, these features are all part of group 44. And you can see from the nominal Kendrick mass, the increase is divisible by 50. These are the masses of the repeating CF2 unit. The column labeled Homologous Series Count shows how many unique masses there are in the series. So if we're looking at group 44, we have 299, 349, 399, and 499. Those are the 4 unique masses within group 44. The column labeled MD filter or mass defect filter shows whether the mass defect after the decimal point fell within the expected range. While this value can be user modifiable in the code or using the modular version as a pop-up, the default captures 90% of the compounds in the EPA master list. The remaining compounds generally have a high proportion of hydrogens or iodine or other elements, which contribute significantly to the mass defect. In this column, confident ID, it means that there was a 1_ value. This means that the chemical was confidently annotated using fragmentation from literature or in-house standards. You can go back to the column labeled ID ranked to see this. Anything labeled false did not have a value of 1_, meaning that the ID is more tentative. The columns labeled 2+ and 3+ homologous series, we show that there are 2 to 3+ repeating CF2 units in the sample. One factor of the scoring is based on the number of repeating CF2 units, so this column can help further clarify a compound's score. Exact mass match simply means it had an exact mass match. Anything with an MS-MS ID will have an exact mass match, but some things without an MS-MS may or may not have an exact mass match. In the column labeled score, you'll see the score rankings from the Kendrick mass graphs ranging from A+ being most confident to E being least confident. Generally speaking, a score of A represents confidence in the structure with a few exceptions, for example, the inability to discern straight chain from branched PFAS. A score of B represents a tentative structure based on some MS-MS evidence and an exact mass match. The structure assigned is a good starting point, but may not be the correct annotation. As with A, scores of B are further subdivided by whether or not the compound occurs within a homologous series. A score of C means these compounds fall in a series with A or B, so the structure may be the same as other compounds with MS-MS evidence, but with a different length of CF2 chain. It is important to note that there are many cases of these exact mass hits not being PFAS at all, and therefore these results are tentative. Score D are assignments with any MS-MS annotation and without other members of a homologous series containing MS-MS annotations. These compounds, though, are possible PFAS and potentially new or unknown PFAS not found in databases. Score E does not fit any of the criteria mentioned above and hence are not likely PFAS, although some exceptions do exist. In the next column, labeled Score Description, this breaks down why the score was given. If you have questions about the specifics of each score, instead of having to look back at the PowerPoint graphic I just showed you, you can look here. This is a useful column to help explain the ranges of each score, and this column breaks that information down into an easily readable format on the table. If you need more specific information on the breakdown within each letter score, you can find that in the FluoroMatch 2 Word document. And our last column, labeled RT Series, shows that when you look at the 2D plots of a homologous series, the hits should fall along the plot in CF2 intervals of 50, which is the Kendrick mass defect, but it should also follow a retention time order. If a feature is flagged as not ordered, you can go back and look at the individual retention times and find out which hit was out of order. This doesn't necessarily mean that it's wrong. It could be a branched isomer, but generally these hits can be considered false. In the column labeled Needs Validation, you'll see a yes or a no. As a new user, it's not best to simply trust the output of the software or any non-targeted mass spectrometry software in most fields. There are a lot of layers of evidence that one needs to dig through to know if a PFAS identification is truly correct. We provide a lot of that info in this output table. If you see a yes in the cell, the annotation can simply be thought of as a starting point. In most cases, you will need further evidence before reporting the structure. You will need to further validate the ID of the class name or formula of the assigned feature, for example, using standards or by manually looking through the evidence. Looking here, you'll see that rows 2 through 5 all need validation. Their scores are C+, which isn't a confident ID. Row 6 has a score of A, and this is a confident identification, and it does not need further validation. Numerous studies applying FluoroMatch show that features are accurately identified over 95% of the time when a score of A is assigned, and therefore these do not need further validation. Note that there are minor differences, such as straight-chained versus branched isomers, that cannot be determined using MS-MS evidence in many cases, and therefore the structure is correct in terms of number of repeating units in class, but not exact structure. This output table that we just went over shows information for one repeating unit. In the case of multiple repeating units, interpretation is exactly the same. Let's take a look at an example of an output sheet when multiple repeating units are searched. The name of the repeating unit is added to the column headers so you can see lines of evidence based on each type of repeating unit. And we are done. Please rewatch this video as many times as you need and feel free to reach out if you have any additional questions. And as always, we want to say thank you to Innovative Omics for their training, access to experts, and cutting-edge resources. Should you need, feel free to visit their website and use this page for contacting them. Thank you so much.